So because we have a lot of syllabus to cover, it's very difficult. So we have been discussing about, if you recall what uh, we have discussed about the uh, effective stress and the quicksand conditions. I have shown some videos like how the effective stress becomes zero. It is a boiling sand, okay, and how we can find out this discharge under the or pressure under the dam by using the flow net and all. I have shown some video, okay. So that particular chapter you can go ahead with that. So that is very simple thing, okay. Then we have seen something about effective stress. So coming to that, just to show you first, second, third, fourth, fifth, sixth, seventh, eighth, ninth CPS analysis. We have seen that, okay. So we have to we can draw the flow net of equal head, and we can have this particular, what do you say, videos I have shown, and that chapter is very small one, okay. And equipotential lines and these streamlines, okay, and there are characteristic of these things, okay. We can find out the discharge, CPS, and pressure by using this flow net and all. And we have seen the effective stress also, quicksand conditions and so on. So what we'll do is today we'll focus on this 11th chapter, okay, that is stress due to loads. So till now, whatever you listen very carefully, okay. This chapter is also very important. You can see some questions in competitive exams, gate and all, okay. So in this particular chapter, uh, uh, we will study the stress due to applied load. So whatever we have seen here in the effective stress, that is what is the load due to the self weight of a soil. Hope you are following, right? That is at a ground without any weight. Self weight is there. How we can find out the effective stress at a particular depth? Gamma into h. H is the height. Gamma is the unit weight of a soil. That soil unit weight can vary. Okay, it can be gamma chat, gamma w. So if it's water, only water, then gamma dash, that is submerged, or gamma dry, and so on. It depends on the soil. But you should remember that the effective stress is can be find out, or total stress, you can say. Total stress is whatever stress you feel at the bottom, okay, with the depth h is equal to gamma into, gamma can be saturation, okay, gamma into h, okay. If you deduct pore water pressure from that, it will give the effective stress, okay. And this effective stress is very very important, okay, for our construction, okay. And we have seen how the effective stress changes with the water table and capillarity, because of capillary water and so on. And again, I have shown you the some videos about the flow nets, bottom of this particular dam, okay. CPS takes place, okay. So hundreds of thousands of streams, uh, water passes through that particular path, and we will take some flow nets, okay, and equipotential lines where the pressure is constant, okay, equal pressure, contours, like we can draw it, and from that we can, by using the Darcy's law, we can find out the discharge, what is happening through it at the CPS. So these things are required for our design and all, okay. So now in today's class we'll see something about the stresses due to applied load here. That means we will try to apply some load, then how the stresses will changes. That's what required for us, okay. And in this particular chapter there are some theories given, okay. They have derived the equation and they gave the direct equation to us, okay. So you cannot find a derivation of this equation. So based on their research work, okay, so this particular book has given some empirical, or you can say derived equations, those who are derived in the previously and given it, okay. So what we are going to discuss today is eh, stresses due to applied load. Okay, that means we are applying some load, a surcharge load, or point load, or uniformly distributed load, or some load we are applying on the ground. Then what will happen to the stresses, that we are going to see it. Okay, that is the 11th chapter. and you try to read because you try to learn the subject. Otherwise you cannot clear any exam if you just simply browse from the internet and get the 19 or 20 marks. Okay, that is of no use. You may get good grade but you cannot clear the competitive exam. That's my uh, suggestion to you. Okay, to clear competitive exams, to get some public service job, you have to study in a such a way that without any this one, okay, browsing, you should answer it. Okay, otherwise it is difficult. Okay, you cannot clear any gate or any exam which is applicable to PSUs and the other competitive exams. Okay, so for that you have to prepare well. Okay, now you may be browsing and just writing your answers, okay, without understanding the subjects, but you are cheating yourself. Okay, later on you will realize because the time may not come back. Okay, once you studied it this year, it won't come back. So you have time, you can just learn the subject, which is very very important. So here, yeah, so this is stresses due to applied load. Okay, so just listen. Generally, here we how we can find out the uh, modulus of a soil. Generally, if I ask you how generally we find out the modulus of a soil, generally general whatever modulus, any materials we can find out the modulus, right? Like stress and strain, you just draw it. Okay, and the slope of this particular tangent will give the modulus, elastic modulus. You might have studied in your strength of material. Soil modulus also can be found in such way. But we generally what we do is, okay, in the soil modulus we have different types of initial modulus and second modulus and the like that we have something. Okay, so generally we consider this second modulus. Okay, here we draw a second and draw the slope of this one. Okay, that would be taken up one third of the total one. Okay, total whatever you get it at the failure. Okay, so since and we can find out the Poisson's ratio also. Poisson's ratio also given in this particular table. Okay, so these are the typical values for the soft clay. Generally it would be 1500 to the 4000. Okay, so e values. Okay, e value soil modulus or Young's modulus you will say. Okay, then hard clay, it would be 6,000 to 15,000, and silty and so on. So these values are given. And we need this Poisson's ratio also. What is the definition of Poisson's ratio? Lateral strain to the longitudinal strain, okay, ratio, and which it can be 0.4 to 0.5. What is the maximum value of Poisson's ratio? Can anyone answer? Hope you are studying Poisson's ratio. Strength of material, whether you are studying strength of material now or mechanics of solids. Am I audible? Please answer.
0.5.
Okay, that is the maximum value. Whether you are studying strength of material in this semester, which semester you are in?
The fourth.
Fourth. Whether you have finished strength of material or mechanics of solids?
Yes, the previous semester.
Yeah, yeah. So that you will understand what is the stresses and principal stresses and so on, right? Hope you will understand. Okay. So same, the mechanics part is same. Okay, whether it may be solid mechanics or soil mechanics. Okay, what generally we do is we will take a small element, okay, at a depth of some h, and we will analyze it. What are the stresses acting in that particular element? Generally, the confining pressure and the shear pressures. Okay, confining the shear stresses and the confining shear. Similar way, same thing. We'll just do all this analysis. Okay, and we can find out the stresses. So geostatical stresses, okay, generally these are the horizontal stresses. Okay, When the ground surface is horizontal and the properties of soil not changing along the horizontal plane, the stresses due to self-weight are known as the due to self-weight, okay, geostatic stresses. And this already we have studied, okay. Vertical stresses, we know, we have taken a small, this one, okay. And how we can, so this is how generally we take the element, okay. We know that vertical, this is sigma y is the vertical, sigma x is the horizontal stresses actually. So whatever in the previous chapter, which one we have studied, vertical stress we have studied. Is it not effective stress or total stress or whatever we call it as a vertical stress? That means what is the vertical stress below h depth, or gamma is equal to gamma into h, okay. Now because soil element is like a cube, like, right, assume, we will assume it like a cube, right. It is having 1 2 1 2 3 4 5 6 sides, okay. So in that case it is three-dimensional problem, this is a three-dimensional problem. So in that case, for our for our comfort, we can make it two dimension also, x and y also, we can make it as z plane also, we can make it, okay. So vertical stresses, still know whatever we have studied is vertical stresses. We can study the horizontal stresses also actually. So those horizontal stresses that you will study in the geotechnical engineering 2 or soil mechanics 2, okay, in the next semester. So now we will just focus on this vertical stress only. So vertical stress, that's what it is given. Okay, well, this thing we have derived it. Okay, so different layer gamma into h. Okay, here the depth. So I want to find out this vertical stress here. What is the vertical stress? If you know the unit weight of this particular soil multiplied by the h, the depth, it will give the sigma y. Now there are the coefficients, okay. How we can find out the horizontal stresses here now? Sigma x, if we ask you, sigma x is just correlated to the sigma y only, because it depends on the y only, okay. If this is more, this would be more. If this is more, this would be more, okay. So because all are confined, is it not? If this is small, this would be small. So likewise, it is, we can say directly proportional to z, then we can write with this particular constant, that a k, okay. That, or we can say that this k is the sigma x by sigma y, okay. So the ratio of horizontal stress to the vertical stress is known as the coefficient of lateral earth pressure or lateral stress, okay. So to find out this horizontal stress, hope you are following. Till now whatever studied was vertical stress. That means vertical, just keep your palm or hand there, whatever you feel is vertical. But we have stresses in the all three dimensional also, right? Horizontal stresses we have. Again, the one more plane we have, three orthogonal plane we have, stresses planes we have. In that case, suppose if I ask you to find out these horizontal stresses, generally would be, it can be xr, sigma xr, sigma z also, okay. Can be find out with multiplication of this particular k. Okay, this particular k. So this k value also can be find out already, okay. This is called the coefficient of earth pressure at rest. If the soil is at the rest, then what happens, this k is equal to k naught. Generally we represent with the k naught, okay. So uh, now I will ask you one question, okay. Where you will find out this sigma x, sigma x reduces, where we can find out sigma x reduces. Imagine one some embankment, or you can say wall. One wall is there, behind the wall soil is there, okay. Imagine one retaining wall, behind that we have soil, okay. Now soil is at the rest. Okay, then what happens, this soil will try to push the wall, that we know already. The soil will try to, because behind that one the soil will, in a sloping ground, you can imagine, okay, on a sloping ground, I want to construct a road, okay, some northern region, northeast region, where we have so much problem, okay. So what generally we do, we provide these retaining walls, okay. In the retaining walls, we will why retaining wall is provided to, retain the soil, I mean to construct this road, we have to stop that particular slope mass. Okay, so what is happening is that whole mass will try to apply force on that retaining wall. Then what happens, sometimes these retaining walls will try to move little away. In that case, these horizontal stresses will releases. The stresses like sigma x in that particular soil will reduces. Hope you are following. Okay, imagine. So likewise, and this cannot also can be found. Fine, that's what I was asking. The strain in the x direction is given by using the theory of elasticity or mechanics of solid. Okay, so Ex can be written in this way by using the Poisson's ratio. Okay, so this you might have seen in the strength of material. Okay, then for the conditions of no lateral strain, when make it this is called 0, then automatically what you will get this equation. Okay, and if we have sigma f, taking sigma x and sigma y. Okay, suppose if it is equal, then this particular k naught we can find out. Understand? That means k naught is equal to mu by 1 minute. So this particular equation is very very important. They will ask in all exams. Okay, k naught is, what is k naught? How we can find out the k naught? Okay, if you know the Poisson's ratio, again it depends on the Poisson's ratio of a soil. Okay, so likewise we can, once you know we k naught or k naught, sometimes it is equal to 1 minus sin phi also. Okay, so k naught is equal to, it can be written as 1 minus sin phi also, and there are values also given about this k naught. That means what you are learning is, once you know vertical stress, we can find out this horizontal stress. Once we have this particular what do you say, uh, particular value of this k naught. Hope you are following. What I'm trying to tell is, once you know the vertical stress and once you know the values of k naught, we can find out the horizontal stresses. So k naught values are given for different soils. Okay, this k naught value is changing for different soil. Okay, so it can be loose sand can be zero point 0.5. Okay, and the dense sand can be zero point 0.3 to zero point 0.5 and so on. Okay, so likewise we can find out this k naught. Understanding? So likewise, okay. Now there are theories which, hope you are following what I'm trying to tell is. Okay, till now whatever we have discussed is, in the 10th chapter we learn how to find out the vertical stresses. In the 11th chapter what we are doing is how to find out the horizontal stresses plus how to find out vertical stresses if at all some load is applied. Load can be concentrated load or any load. Okay, so till now whatever we have studied is how to find out the horizontal stresses. How to find out the horizontal stresses? Once you know k naught value, multiply the vertical stresses will give the horizontal stresses. Once you have k naught value and if it is multiplied with the horizontal vertical stresses at a depth z, we can find out the horizontal stresses also. Now let us see this particular theory. This guy, this person, the Bushness, okay, gave a theoretical solution for this. Okay, vertical stress due to constant. Now we will focus on the load applied. Okay, so vertical stresses due to concentrated load, like we'll see in the beams and columns or buildings. First, what we'll do, we will try to apply concentrated load, and we'll find out the shear stress, bending moment, and so on. Okay, that in similar way, what we'll do is we'll try to apply a concentrated load. So here, what I'm doing is I'm applying. This is the plane. Okay, this is the ground. I'm applying a concentrated load Q here. Okay, at a depth z. Okay, what I'm doing is I'm assuming one point here P. Okay, not exactly below that Q. Okay, exactly below that will be exactly will get when may R becomes 0. Okay, you will get it that one. Okay, what we'll do is little away from the particular applied load. Okay, here little away from that. How much away? let us take a one coordinate, okay, x, y, and the r is the orthogonal coordinate, and which makes a angle beta here. Okay, so I'm choosing a point P here. Try to understand. Okay, what I'm doing is now I'm going to find out a stress due to applied load. What kind of load that is? Applied load. Self weight we have seen it, gamma into h. But if you have some weight applied load, that is q, which is a point load, suppose if it is a point load, then I want to find out the stresses, vertical stresses at a distance, at a depth z below the ground. But what we are doing is at a away from the that particular point load, at a how much away? X, y, and the z are r coordinate away from that. Understand? So what business says, he has given these particular equations. Okay, this equation he has given. So what he says, Business proved that the polar stress, that means this P, okay, from here at orthogonal distance of R at a point P. Where is that point P? X, Y, Z coordinate is given by this particular equation. Understand? So he derived it. So in the book, in this book, particular book, we are just seeing that equations. What he has done is, what he says is this particular stress. This particular stress is uh, at a distance x, y, z at a point P can be written as 3 by 2 pi q cos beta. Beta is the angle and the r square. Where what is the r here? Polar distance between the origin O and the P. Beta is the angle which the OP makes with the vertical. And obviously we can write this r. R is equal to how much? X square plus y square plus z square, or you can write it on x square plus r square. Okay, r is nothing but the x square plus y square. What is sine beta? R by capital R. What is cos beta? Z by R. Is it not? So what he says is the vertical stress. This is the polar stress. Okay, the vertical stress gamma z at a point P, again he says, would be equal to this polar stress sigma r multiplied by cos square beta. Following? So this vertical stress at P, okay, polar stress, this is a sigma r. Okay, then which is perpendicular to this one. Okay, now this vertical stress sigma z can be written as sigma r into cos square beta. He says it would be this much. Then sub sigma r, we know that we find out from this equation. You substitute this one, and finally you simplify that, you will get this particular equation. So sigma z is equal to, okay, at a distance z, okay, below, can be written as sigma z is equal to ib into q z square. What is ib? Just 3 by 2 pi 1 plus r by. So these equations are very very important. Sometimes they will ask question from this one. Okay, they will give r, they will give z. Okay, away from this one, r distance from particular point, and z distance below the depth. Okay, what is the sigma z? Okay, sigma z equal q by z square. Z is the depth where we want exactly to find out. So this particular equation is simplified with this factor that is called ib. So this, so it would be easy for to remember, right? So q by z square, if you remember, and multiplied by I by ib, that will give the vertical stress at a depth z when point load is applying. That you should not forget. So what is this IB? IB value also given. Okay, the coefficient IB is known as the Business influence coefficient for vertical stress. The value of IB can be determined from the given the values of R by Z Okay, the computed values are like this. Okay, R by Z for different R by Z, R by Z, R by Z. What is IB, IB, IB? You can find out. Okay, and we can apply here, and we can find out this particular particular stress due to point load. Once we know the R, okay, polar distance, and at what depth Z. Okay, once we know that, by using this equation, Bushnell's equation, we can find out. Hope you are following. Okay, read it. It's very simple thing only. Okay, so there are limitations for Bushnell's equations also. It is given. Okay, uh, limitation. The solution was initially obtained for determination of stresses in elastic solid. Its applicable application to solid may be questioned, and there are some limitations also given. Okay, uh, the application of Bushnell solution can be justified when the stresses changes are such that only a stress increase occurs in the soil. So the real requirement for such solution is not at all soil is inelastic, because thing is whatever we are giving that, but soil is not a homogeneous or isotropic material. So whatever theories we are just proposing it may not give the proper result. Now horizontal stresses and the shear stresses due to concentrated load. Now till now what we have seen is vertical stress we have seen. Now what I will do is horizontal stresses. That means imagine a small element here. Okay, small element, and this element is having all the stresses, like vertical is there, tau zx, tau zy. Okay, so here 3, here 3, and here 3, all 6, 9, we have all 9 stresses. Hope you are following. Okay, what we are finding is vertical, horizontal, and the shear. If you find out these stresses, okay, then it is very easy to understand that how much stresses it would develop. Okay, because it all depends on the h value, that is the RS z value, that is at a depth of z. So what he has given again, this Bushnell is, so what he says, again he taken an element. Okay, and for horizontal stresses sigma s, he has given this equation, very big equation, he has derived it. Okay, likewise he has given for the sigma y also, like that he has given for tau xy, tau yz, tau x x zx. Understand? That means once we know this uh, q value here, q value, once you know the z value, once you know the r at what distance it is there, okay, we can find out this tau x, tau y, tau z, and all the stresses here. Understand? What we are doing is, when we are taking a small element, that element would be cubical form. In that cubical form, we have not only vertical stresses, we are assuming all the vertical, all the shear stresses also. That means sigma x, sigma y, sigma z. These are the three confining pressure, you can say, confining sigma x, sigma y, sigma z. Three confining four stresses on a small element confining stresses sigma x, sigma y, sigma z, and confining. In addition to the confining or stresses, there would be shear stresses also in the element of a soil. How to find out those shear stresses? Bushnell has given the equations. Okay, what are those shear stresses? In this plane, if you see tau yz, tau yx, here tau xz. So this tau z, this will be equal. Okay, that's the reason. Ultimately, this unknown things would be 6 only finally. Okay. So again, in a cylindrical coordinate also, they have given this particular sigma x, sigma r, sigma theta, and so on. The equations are given, radial stresses, and this one. Okay. Now coming to this particular uh, uh, isobar diagram. So what is this isobar diagram is all about is, if you draw stresses, okay, and if you draw a line of equal stresses here, okay, equal stresses in the sense of same intensity. Suppose if you draw, and if you are able to draw this particular bulb here, this is called the isobar diagram. Okay, like a bulb below that here. Okay, of equal stresses, vertical stresses below the ground. Okay, below the ground because of this load Q, there would be some stresses below the ground. Okay, if you are able to join the points of equal stresses intensity, okay, in other words, an isobar is an contour of equal stresses. Okay, if you join all these things, that particular bulb, whatever you find out, is called the isobar. Okay, this particular, so they will ask in the exam, complete exam, what is this isobar diagram is all about. Can you define the isobar diagram? Okay, so they may ask, isobar is the curve joining the points of equal stress intensity. Okay, in other words, an isobar is a contour of equal stresses. Okay, so anyway, we'll see this one. So till now, whatever in today's is the how to find out the horizontal, vertical, and the shear stresses by using the Bushnell's theory. Bushnell has given some equations. Based on that, we can easily find out, once we know this particular z at a what depth we need it, at a what distance, x, y, z coordinate. If you know x, y, z are the orthogonal r, if you know it, if you know these things, and if you know the q, how much point load you are applying, how much point load you are applying at and at what depth you need the stresses, and whether you need exactly below the point load. If you want exactly below the point load, what you have to do is x, y, z, r, you have to make it 0. Okay, you will get r in gamma into h. Okay, so likewise, and at what distance, radial distance, you want to find out this if stresses. Okay, so till now we are not talking about these are the stresses only. Okay, now we are not involving any water table or gamma set, just stresses, you can say. It can be bulk stresses. Okay, bulk. Those things also we know it. What we do with the gamma, if we get gamma set, we use gamma set. If it is a bulk, we use gamma bulk. If it is a submerge, we will use submerge, and so on. Okay, so just find out that if you know the gamma, and if you know the q value, point load, at a what distance you need it. Bushnell has given the equations for the sigma x, sigma y, and the sigma z, and the tau xy, tau xz, and tau zx. All three, all the parameters, he has given that equation. So by using those equations, we can find out the stresses due to applied load. What kind of load? Today we have seen only point load you have seen. Okay, so with that I'll stop today. You please read it, you will understand. It's not very difficult. Okay, it involves some equations. So I'll stop today. Okay, already 10:10. So please read the Aurora book. Okay, it's very good book. So I'm going to end the meeting. Okay, thank you.